Okay, finishing up the Green's theorem idea. Our fourth example says we want to evaluate the integral over the closed positively oriented curve um, y squared dx plus 3xy dy, where C is the boundary of the semi-annular region D in the upper half plane between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. That whole semi-annular region is actually something I had not heard of before, but this is what we're looking at. So it's in the upper half plane between the circles x squared plus y squared equals 1, something like that, and then x squared plus y squared equals 4, looks something like that, where that's 1, that's 2, 1, 2. Let's make those negative just to be right. All right, and the region is supposed to be where C is the boundary of those two things. So it looks to me like this is the region that we're talking about here, going this direction. And I know that it has to be going in this direction because it does say that this is going to be a closed, positively oriented line integral. So what we are going to need using Green's theorem is the double integral over d of dq dx minus dp dy dA. So I need dq dx, and from here, dq dx, so the derivative of that thing with respect to x, I'm sorry, that's dp dy, I apologize. dp dy, because that's p, is going to be 2y, and then here we'll get dq dx, and that's with respect to x, so that's going to be 3y. Okay, so these are circular, so there's absolutely no reason not to go with polar here. So when I set up my double integral, let's see, it's going to be, r is going to go from 1 to 2, and theta is going to go, it looks like from 0 to pi. Doesn't go all the way around this time. All right, so dq dx, that one right there, that's 3y. So in, actually, you know what? Let's do it this way. Since I know it's going to be dq dx minus dp dy, well, that's just going to be 3y minus 2y, so that's y. That makes this a lot easier, because y is just going to be r sine theta. So I'm going to be doing r sine theta, r dr d theta. So we know we're going to have the integral from 0 to pi of d theta times the integral from 1 to 2 of r squared dr. 0 to pi for d theta is just going to be pi. This is going to be 1/3 r cubed from 1 to 2. So we're going to get pi times 1/3 of 8 minus 1, or 7 pi thirds. And that is totally wrong. I apologize. Hopefully you guys caught my huge mistake there. I completely neglected the sine theta. So it won't change the r part, but it certainly is going to change the theta part. So that's going to be negative cosine theta from 0 to pi. Plugging in pi, cosine of pi is -1, so that becomes +1, minus, plugging in 0, that becomes -1, so you get 2 there. So that is completely different. There's no pi involved in this at all. Let's get rid of that. And that becomes 2 times this whole thing. So instead of pi on top, we're now going to have to multiply it by 2. So we get 7 14/3. Sorry about that. Easily correctable mistake, though. All right. Example 5, use Green's theorem to evaluate the line integral f dot dr. Check the orientation of the curve before applying the theorem. So we're given that f is e to the x plus x squared y, comma e to the y minus xy squared. That is our vector field. And our curve is the circle x squared plus y squared equals 25, oriented clockwise. So they actually tell us the orientation of this circle with a radius 5 is oriented clockwise, so it's going this direction. Well, that's backwards. We don't want it to be going that direction. So C is actually going in the wrong direction. So remember that if we have the line integral over a C which is going in the opposite direction of f dot dr, we can say that that's the same as the negative integral of C in the correct direction of f dot dr. So in order for me to change this into the correct direction, what we needed to do is change the whole integral to negative, and now the C is going in the correct direction. So our double integral here is definitely 0 to 2 pi. That's in the correct direction. R is going to go from 0 to 5. We're going to need dp dy and dq dx. So let's go ahead and grab those real quick here. So didn't write that right, dq dx does not look like a q. Still doesn't really, but that's close enough. dq dx, so in this case, this is p, this is q. The derivative of this thing q with respect to x, the e to the y goes away, so we're going to get negative 2y. And then dp dy is the derivative of p with respect to y, so the e to the x part goes away, and it looks like we're just going to get x squared. All right, so we need to do dq dx minus dp dy. What did I do wrong there? I'm making all kinds of mistakes here, aren't I? dq dx. dq dx. The derivative of q with respect to x is negative y squared. Hopefully you're watching this at like 4 times speed, and the mistakes seem like they're really small. Okay, so that's right. So now remember that dq dx minus dp dy, in this case, is going to be negative y squared minus x squared. Well, that's the same thing as negative of y squared plus x squared. And in polar, that's going to be negative r squared. So I'm going to throw the negative out front here, and I'm going to have r squared there. And then don't forget it's r dr d theta. All right, so this time I don't have any kind of trig functions in here. So I do have the negative of the integral from 0 to 2 pi of d theta times the integral from 0 to 5 of r cubed dr. So the 0 to 2 pi part is going to give me negative 2 pi and this is going to give me 1/4, oops, no integral, 1/4 r to the 4th from 0 to 5. So that's going to give me negative 2 pi times, let's see, 5 to the 4th is 625 over 4. That 2 out front is going to simplify with the 4, so we're going to get negative 625 pi over 2. And I made another mistake somewhere. Oh, here it is. That was negative r squared. So I forgot to put the negative here, because remember that this double integral right here already has the negative sign there because we're going in the correct direction now. So that's going to make that positive, 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 positive. So it should be 625 pi over 2. All right. Last piece. Big concept here. What if d is not simple? So remember that the idea was this. If you have some kind of a curve, some kind of a closed line integral idea here, this would be simple. There's no holes in it, there's no breaks, there's no openings, it's a simple curve. But what if I threw in some kind of a hole into this thing? So this is no longer a simple one. So here's what we can do, because everything that's up there is part of the boundary, which includes that interior part. That's still part of the boundary of this curve. The problem is it's not connected. So here's what we can do. And this is kind of an interesting concept. I can take and kind of do an imaginary line at some place in between those two things right there. And what I can do is I can basically say that this down here, all of this space in yellow, see if I can get that whole thing filled in. I made this way too big. But all this space here in yellow would basically be my D1, like a domain number 1. So all that in yellow is like domain number 1. I could also take all this space up here in blue, and we're going to call all the space up here in blue domain number 2. Once I get it kind of all filled in there. So we'll call this up here domain number 2. So what you get by separating it by that green line in the middle there is I get 2 simple closed regions. If I look at just the D1, it's now a simple closed region. If I look at just the D2, it's also now a simple closed region. As a matter of fact, all of this is part of D1. All of this, oops, kind of went way off the line there, is part of D2. So if I want to take and use Green's theorem, I can traverse D1 in a counterclockwise fashion. And hopefully you can agree that all of that, if I went counterclockwise, I could use Green's theorem and go ahead and find D1. But you might be thinking to yourself, well, now wait a minute. That's fine, except we arbitrarily just threw in some extra boundary lines. Those green lines, we just arbitrarily threw those in. Those are really not part of the boundary of this closed or non-simple closed curve. And you'd be right. But watch what happens. If I went on and tried to find the line integral portion of D2, going again in a counterclockwise fashion, look what happens now. All of these things are going against the green until we get back to the actual portion of the graph, and then against the grain here. So in essence, this and this, because we're traversing it in opposite directions, are canceling each other out. Those imaginary boundary lines will cancel out. So what we get is two simple closed regions. And the ultimate takeaway from all this is that Green's theorem will still hold true. So if we have a non-simple region, we can create those imaginary boundary lines, and then when we traverse those things using two separate Green's theorem integrals, the two boundary lines are going to cancel themselves out. And then we would add the two together, and we would get the line integral over that region, even though it is not a simple closed region. All right, that is plenty enough. It's way longer than I wanted to. Apologize for the mistakes. Hopefully that helps explain what is going on.